Okay. All right. Good afternoon. Let's continue on with our discussion. Well, unless you all want a refresher, Kevin and Norton. Uh, yeah. All right. Let's see. 21. And we were discussing the basic operation of a NPN BJT. Right. We have three terminals: collector, base, emitter. Collector, base, emitter. We have charge carriers going through the junctions, and we have three currents associated with each one of those terminals: the base current, collector current, and the emitter current. And as this illustration shows, the emitter current is a result of the combination of IB and IC. So IE is basically IB plus IC. And in this illustration here, we looked at a little bit of the semiconductor physics or device physics of how an NPN transistor would operate. All right, so before I move on, any questions? I know we were rushed a little bit at the end, but did that explanation make sense? Right, on why we have a one junction forward bias and the other junction reverse bias, and the operation of the transistor depends on the actual physical construction of the device, as well as the amount of doping or the amount of impurity doping that we do on each one of those junctions. Right? Otherwise, the transistor wouldn't work. Okay. All right. So moving on. There are parameters associated with the currents that flow in a BJT, in a transistor, right? And the most important one is right here. The two parameters are known as alpha and beta. Beta is defined as the current gain of the transistor. Okay. Actually, let me go back to this diagram right there. Now, what do you see about IB? Just indicated by that small arrow. Like the thin arrow. Remember, I said the base is lightly doped, meaning it does not have as many carriers as the emitter, right? So the base current is typically very small. Base current is typically very small. So even the arrow marker notations that you have in there, they have certain meaning. So the base current is typically small, whereas the collector current is quite large. Okay, the base current is very small while the collector current is very large. And the collector current depends on the base current. So the ratio of the collector current to the base current is noted by the quantity beta. Ratio of the collector current to the emitter current is noted by alpha. Emitter current is equal to IC plus IB. IB is typically very, very small. So IC and IE are very, very close in value. Typically, IC would be just a tad smaller than IE. And so the ratio alpha is typically very close to like 0.99. Okay. IB is typically measured in microamps. It is that small. And the collector current and the emitter current, IC and IE, are typically in milliamps. Okay. So the ratio of IC to IE is around 0.99 or so. It depends on the problem. Yeah. Beta, again, as I said, the single most important quantity is known as the current gain of the transistor, and the typical value for beta would be from 10 all the way going up to 1000, depending on the design of the device, and how you configure the transistor. Typical values is about 100. Could be anywhere from a 10 to 1,000. Typically is about 100. You apply a very small amount of current at the input, and you get a very large amplified current at the output. Okay. And of course, from those two equations, we can also write an expression relating beta and alpha. So beta is equal to alpha over 1 minus alpha. Simple equations, nothing too strenuous. Straightforward examples. Let's see. Seem to have left my notes. There was an example that I was going to do, but I don't have the notes in front of me. But basically, the examples were you were given the emitter current, or you were given the collector current, or the base current. So you have three currents: collector, base, emitter. You're given like one or two of the other three, and you are asked to find either the alpha or the beta. Those are the examples. So the homework number 5 deals with BJT fundamentals, and basically there's a extra credit tutorial as always in there, and there's some simple problems that deal with the fundamentals of these BJT parameters. Okay. Yes. Saturday. It's already available, but it's like 30, not even 30 minutes. The extra credit tutorial is long because it's a tutorial, but the problems themselves are like just the first 2 or 3 problems are like multiple choice. After that, it's like simple calculations like these, just to get students familiar with, the fundamentals. Yes. No, I left my notes in my office. That's why. I had an example in my notes and don't have that with me right now. Yeah, I'll post it on Canvas if you want. But it's a simple example. You have 5 quantities: IC, IB, IE, alpha, and beta. And basically, we have the equations. So depending on what you're available in the problem, you calculate, just plug and solve. Rather straightforward, simple math, if you will. Okay, so based on the biasing conditions of the BJT in the circuit, we have 3 different modes of operation. Okay, 3 different modes of operation. We have cutoff, saturation, and active. Cutoff, saturation, and active. Okay, and each one of those has a separate application. Here, right at the bottom where we say active mode occurs when the base emitter junction is forward bias and the collector base junction is reverse bias, which is basically the operating mode that I just explained, right? Where the carriers cross over the junction, go all the way to the collector, and you have collector current flowing through the circuit. In the book, and just generically, it is also referred to as the normal mode of operation. So normal mode of operation. Okay. So active mode is also the normal mode. Basically, the explanation that the device physics explanation that I gave, that is the active mode or the normal mode of operation. And we use that mode when we want to use the BJT as an amplifier, right? As an amplifier. Okay. We'll do an audio check. I just want to do that. And then the other 2 modes are cutoff and saturation. So depending on the biasing conditions, if both of the junctions are reverse bias, we say that the transistor is cut off. Both of the junctions are forward bias, then we say the transistor is completely saturated. As the name suggests, when it's cut off, it's no current flow. When it's saturation, it's completely saturated, that's maximum current flow. And both of those modes put together, we can operate the transistor as a switch, which is another important application of a BJT or a transistor. In reality, the digital logic circuits that we use, like in everyday life, our microprocessor, CPU, all of those, all of their what they're doing is we're just using them as switches, the zeros and ones, right? If it's cut off, it's zero. If it's saturation, it's on, and we say it's one. Binary number system, which we will see in just a few chapters later on in this course. Okay, but two big applications. One is at a switch. The other one is as an amplifier. Amplifier is when the BJT or the transistor is running in active mode. Switch is when it runs in cutoff or saturation mode. Cutoff means it's completely cut off. There's no current flow through the device except for some slight small leakage currents. So we say the transistor is off. Saturation is when both junctions are forward biased, completely saturated, maximum current flow, and we say transistor is on. So it's either on or off. So this so here we would say it's on and off. Oh, the other way around. Off and on. Okay, takes 10 seconds. Let me know if anyone has any questions. I was sore throat from like talking too much over the last few days. Yes. We will look at everything. Yeah. Yeah. So this illustration here, this chart here shows the output characteristics of a NPN BJT. On the x-axis, we have the collector to emitter voltage. That's where we take the output from. On the y-axis, we take the collector current. So it's a plot of how the current output behaves versus the voltage, okay, at the output terminals. Now, this is a characteristic plot for a common emitter configuration. Again, we will look at that configuration in just the next few slides, but I wanted to point out the three regions. Right at the bottom, right here, is where we have the cutoff region. So cutoff region, very minimal current flow. Right, saturation is on the left, and maximum current flow. And active region is here in the middle. That is where we will use the transistor as an amplifier. Okay, so again, cutoff is right at the bottom, very minimal current flow. Saturation is on the left, maximum current flow, and active region is in the middle. We will again do a load line analysis similar to what we did for the diodes and the Zener diodes, and then once we plot it, graphically it'll make more sense on how it works as an amplifier. All right. So any questions about modes so far? Okay. All right. So how do we determine? Well, if both junctions are reverse bias, just by its very definition, if you remember PN junction diode, if you reverse bias it, there would not be any current flow across either one of the junctions, right? So we have an NPN transistor, right? NPN. So, whoa, this. It's gotten completely loose. Let's see. So it's NPN. So if it's NPN, and you apply positive polarity voltage to the collector as well as the emitter, both junctions will be reverse bias. with respect to the base. And if both of them are reverse bias, then the transistor is completely cut off. Yes. Oh, NPN. Thank you. So the collector voltage is higher than the base, and the emitter voltage is also higher than the base. Right? Both junctions are reverse bias. Make sense? Right? It's PN junction, you reverse bias it. The only thing that's flowing through there is a small amount of leakage current. Then both junctions are forward bias. Both PN junctions forward bias, maximum current flow. Collector, again, we have N, P, N. Collector voltage is less than the base. Emitter voltage is less than the base. Both of them are forward bias diodes. Maximum current flows through the device. Okay, and so that is saturation mode. And then lastly, our normal mode of operation, or the active mode. Actually, wait, students will write it down. Okay, wait for a few more seconds. Yes. We'll actually see. So saturation, what happens is both junctions become forward bias, so maximum, so all the charge carriers are free to move around, and so you get maximum current flow. So immediately, for a small amount of current, the collector, all the charge carriers present in the device are able to just cross over the junctions in both directions, and so there's maximum current flow in both directions. It automatically reaches the highest level that the transistor can sustain, and so the transistor completely gets saturated. VCE drops to like 0.2, below 0.4 volts. So the junction is not reverse bias anymore. Well, forward bias junction. Yeah. And then lastly, our normal mode of operation is basically the emitter base junction is forward bias, and the collector base junction is reverse bias. So collector voltage is higher than base, emitter voltage is less than the base, then we say the transistor is operating in the active mode. Okay, transistors are operating in the active mode. Basically, in cutoff, we don't have any current flow. Saturation, you have maximum current flow. Active region, you can actually control the amount of current that's coming out. You can control the voltage, you can control the current that's coming out. So if we think of it, let's see. It'd be hard to show it without any issues. But remember, I said in active mode, we're going to use it as an amplifier, right? So amplifier would be, let's say if we give a small signal like this at the base. Depending on the biasing voltages that we provide, you would expect a output voltage something like this, right? When it's saturated, it doesn't matter what you are providing at the input. You could give an input like this, and your output, because it is saturated, might be like a cutoff version that comes out like this. Or it could just be like a flat DC, because so much current is flowing through there that you could change the input, vary the input signal, but the output will just remain like a constant line. Okay, so you would not be able to modulate the output at all. You would not be able to change the output at all. When we able to change the output, that's where we're using it as an amplifier. Yes. So yes, let me write it down. So this is active. This is not quite saturation, but an approximate effect of what would happen when it's saturated, right? You're so much current is flowing through there that the output's already at a very, very high level. It never drops below a certain level. Okay, so that goes back to the question that was asked earlier. What does saturation actually mean? Well, the transistor is completely saturated, and so it just means that maximum current is, all the charge carriers are just flowing through the junctions because of forward bias, and you have maximum current coming out of the output. And so instead of the output actually being the signal that we want, is basically distortion. It's distortion. It's amplifying so much that the top limit is just getting cut off. And if you it's even more amplification, then the output is just like a flat line. All you would hear is basically like these, instead of like time varying signals, you just see like a flat line. This level comes from the DC voltage that we're applying, right? So the DC voltage we're applying is, let's say, plus minus 10 volts, right? Plus minus 10 volts. But now because of saturation mode, this output goes to like 25. Well, the transistor cannot supply more than 10 volts because that is what we're giving as DC voltage, as the biasing voltage. So it gets cut off and it's distorted. Yes, you had a question? Yeah, it's, what do you mean? Oh yeah, what makes, yeah, exactly. So it's the basically DC voltage, that we're applying. So transistors and amplifiers that we work with, they are actually, let's just talk in generic terms, like amplifiers in general, you receive an input signal and you amplify it, right? The input signal is almost always just AC signal, meaning the voice that I am, that the microphone is recording, the vocal sounds that I'm making, right? Those are AC signals. The microphone converts it into the sound waves into electrical signals. So you take these AC signals, you pass it through an amplifier, you make it bigger, right? Well, the energy to make it bigger does not come from that AC signal. It comes from the DC bias that we apply. So if you have an AC signal coming in and you have a DC biasing that we apply to that amplifier. Does that make sense? Right, so it's a DC signal that comes, so the DC voltage and current that is being applied externally. So what your amplifier is doing is it takes that DC and it takes that AC and it gives the shape of that AC signal to this DC voltage that's coming in. So now your DC, which was a flat line, now takes the shape of the AC signal. Does that make sense? And I just realized that I was just making hand gestures and perhaps online students weren't able to see it. So let me draw it out here. Yeah. So let's say you have a small AC signal and you add it to a DC signal that is at a higher level. Let's say like this, and the amplification result you would get something like this. Yes. It depends on the configuration that we want to use. It's a good question. So the question being asked is which terminals are the input and which are the output? And so we'll talk about that in just a bit. Does this make sense? This is basically the basics. So if you think about it, if you have a, if you have an audio video receiver at home, you'd plug it into the wall. And then from your computer or Blu-ray player or DVD player or gaming system, you connect the output of those systems into the audio video receiver, right? So the signal coming from your DVD player or Blu-ray player is basically this. And the power outlet is providing this DC. And then the amplifier is taking that input signal, combining. I mean, of course, there's a lot of other processing going on in there, but essentially that's what it's doing. It's taking the power from the wall, converting a DC power input with your gaming console or music system or whatever, and it's outputting it to the speakers. All right, questions? Hopefully all of this makes sense so far. I mean, in depth, there's a lot of things. We started with device physics, but now we'll work with like terminal characteristics, meaning we'll work outside of the transistor, not inside. Like we'll work at the terminals. Yes. In generic terms, yes. Yes. If you increase the DC, then yes, it should increase. Power handling capability should increase. So saturation is a condition of the transistor where it cannot operate beyond what it's designed for. Like there's constraints placed on the transistor by the physical size of the device, by the doping, the amount of doping that we do, and the biasing that we give, which is from the DC. So if this signal is large, if the signal is already large, what happens? Let's say this is, I don't know, 1 volt. It's not typically 1 volt, but let's say it's 1 volt. And this DC is 10, right? And the gain of the amplifier is designed to give you, I don't know, the gain of the amplifier is like, let's say 5. So the output of this amplifier, so if gain is 5, then V out would also be 5, right? But if now the gain is 100, circuit design gain is 100, is your output going to be 500 volts? No, right? Because that energy has to come from somewhere, and the maximum DC we are applying is only 10 volts. So it cannot be 500. Maximum it can go is only 10 volts. And so instead of getting something like this, you would have like a huge waveform, but the transistor is saturated, so you only get like this much. So all of this is gone. So all you would get at the output is basically something like this. Everything, all of the other information is lost. All of the other information is lost. Okay. And again, when we look at amplifiers, common emitter amplifier circuits and stuff like that, we'll talk about distortion a bit more. But essentially, that's what happens. Now, this is a simplistic, this is just one cycle of a AC signal. Obviously, AC signals like multiple cycles, multiple waveforms. But essentially, all you're getting is like a flat line, which is essentially DC at the output. There's no variation, right? You'll just get like a bzzz sound coming out from your speakers. So, question was being asked earlier, which terminals are the input and which are the output? Well, we have 3 terminals, right? If one terminal, if one terminal is common between the input and the output, we can have 3 different kinds of configurations. So common terminal between the input side and the output side. Okay, so depending on which terminal is common, we have 3 different configurations. You have the common collector, common base, and common emitter. This diagram right here shows you the common emitter configuration, which is also by far the most popular configuration. Typically, the base current is always the input and the collector is always the output. Okay, so even if it's a common base or common collector, the base current is always the input, collector is always the output. So here, the base emitter junction is the input and the collector emitter junction is the output. The emitter is common to both the input as well as the output. Okay, hence common emitter configuration. If we plot the characteristics for the input and the output, we get the input current versus the input voltage, and we get the output current versus the output voltage. Input side, it is base emitter. Output side, it is collector emitter. And so input characteristic is a plot of IB versus VBE, right? IB versus VBE. And collector and emitter is IC versus VCE. Okay, so the output is taken across the collector. Let me zoom in a bit on there. That better? So input side, base emitter junction, this CE is collector and emitter. Okay, IC versus VCE and IB versus VBE. What do you see? Let's take a look at the input. What do we see? Input characteristics. Does it look familiar? It looks like a forward bias diode. So normal operation, if you want to use it as a amplifier in the active region, base emitter junction is forward bias. Forward bias PN junction should look like forward bias diode drop. So base emitter junction, once it is forward bias, doesn't matter how much voltage you apply doesn't matter how much voltage you apply on the input side. This is typically referred to as VBB, supply voltage VBB, and this is referred to as VCC, supply voltage VCC. Anyway, once that VBB supply crosses 0.6 or 0.7 volts, this VBE always remains constant, right? The forward bias junction, so VBE will always be 0.6 volts, 0.6 to 0.7 volts. Well, for a silicon BJT. VCE depends on whether the transistor is in cutoff or in saturation. Since we're taking the output here, if it's in saturation, maximum current is flowing, then the voltage is not going to be high. In the active mode, it depends on what input we give. So VC would fluctuate depending on the AC signal. Okay. Again, there's a lot of considerations, but we won't, again, for E majors, this is an entire class by itself, entire course by itself. So not going to go deep into it. Just skim the surface, look at the terminal characteristics and operation. Does that make sense? Let's think over it. Let me know if anyone has any questions. How many of you all tackled the pre-lab? Did you all look at the pre-lab, right? Do you all look at the lab write-ups before you do the pre-labs? Most, okay, because I keep telling students in 251, 361, the lab write-ups have all the equations and the information. In this one, it's been a while since I did 361, but once I open it up, I realized everything's there in the lab write-up. Right? Everything's there, all the equations and everything's there in the lab write-up. And we'll look at C amplifiers well, as we go along later on in this chapter. So far we're discussing NPN transistors. I just want to briefly bring up PNP transistor. PNP transistor is exactly the same, no difference whatsoever. The only thing is it now has a N junction sandwiched between two P junctions. The physical makeup is exactly the same. You have a very thin layer of the base, but your starting material is now P or P plus, right? So silicon material is P plus with lightly doped column 5 compound. And you create the opening in there, deposit your N-type material. Deposit your impurities in there to create an N-type material. You create a second opening in the N-type material to deposit heavily doped column 3 compound, right? Heavily doped column 3 element, sorry, not compound. And that would create a P plus plus junction. So this one, I would say it's P plus, N plus, and this would be P plus plus. The emitter has a lot of excess positive charges. The current is now flowing in the opposite direction, which is indicated by the arrow that goes into the device, not out. So anytime you see the arrow going in, that is a PNP transistor. Anytime you have an arrow coming out, that is a NPN transistor. So these are just some of the basics that as non-EE majors you should be familiar with. Okay. All of the current directions are reversed, right? All of the current directions are reversed. Fundamental equations do not change. IE is still equal to IB plus IC. Okay, they do not change. Everything else, the parameters alpha, beta, all of it remains the same. They don't change. Okay, there are still two PN junctions. The modes of operation, everything just remains the same, except everything is now switched. The polarities are now switched. Everything's the same. Yep. Everything. Common emitter configuration for PNP, similar to the NPN transistor. You have two power supplies, but now look at the polarities. Polarities are now reversed, right? You got a PNP transistor. So if you want to reverse bias the junction, you have to flip. The voltage source is now flipped, right? In order to reverse bias this junction. And then right here, this is forward bias. So again, no change in operation. Characteristics are now plotted in the other quadrant because if we take a reference measurement VBE, you measure the voltage at the base with the emitter as your reference, VBE. B is going to be negative minus, and emitter is going to be positive. You still a forward bias diode, but because our reference is B, it's going to show you a negative number right there. So just wanted to explain that. Students typically do have questions about that. Why do we have negative numbers, even though it's a forward bias diode? Well, that's the reason. It's just that our reference point is the emitter when we actually plot it here. That's all. But it's still a forward bias diode, and the collector junction is still reverse bias. Operation takes place exactly the same way. Charge carriers are now switched. Holes in place of electrons, electrons in place of holes. All right, any questions? Most of the circuits that we look at will all be NPN. Okay, PNP is just, again, as I just wanted to introduce the topic, a non-EE measure class. We do not go too deep into all of these operations. Even in the lab, the transistors that you use are NPN transistors. So the C amp, yes. They are used. I mean, wherever we use NPN, we can use PNP transistors too. Yes. Yeah. It's not as if they are not used or never used. They are used. Okay, summarize the operating modes for both transistors. We have cutoff, saturation, and active. And these diagrams are just showing you for the polarities for both NPN as well as PNP. Okay, this handy dandy table just tells you which junctions are forward bias and which ones are reverse bias for each mode of NPN or PNP. So emitter based junction, obviously for a NPN transistor, needs to be reverse bias. Collector based junction is of course reverse bias, then it's cut off. The collector based junction is forward bias, then it goes to active, right? And then same thing for the PNP transistor. So only thing is polarities are flipped. All right. Let's see. So if you want to determine the operating mode for a circuit, what do we need to do? Well, we don't need to analyze everything in detail, but just in general terms. Exactly. Yeah, we measure the voltage and then look up at the table and we can see whether it's forward bias or reverse bias, and then whether it's in cutoff or in saturation. So if we notice, the first thing we can do is check if the emitter based junction is forward bias or reverse bias. Because right off the bat, if it's reverse bias, we can automatically eliminate two of the modes, right? So the first thing we do is we check the emitter based junction. If the emitter based junction is reverse bias, then right away we can say it's in cutoff. Right away. If it's forward bias, then we check the collector junction. And then if the collector junction is also forward bias, then it's in saturation. If it's in reverse bias, that's normal mode of operation and it's in active mode. And that's it, as straightforward as that. Okay. So when you're analyzing a circuit, again, don't worry about everything else. There are equations that are associated with this. But when you're analyzing a circuit like this, you obtain certain voltages. We measure the voltage at the base, measure the voltage at the emitter, the collector, and we check the voltages in relation to each other. First thing to check, if you want to check emitter base junction, well, what is the emitter voltage right here? 1.3. Base voltage is 2. What does that tell us? Base is higher than the emitter, right? If base is higher than the emitter, N transistor, P is higher than N. Is it forward bias or reverse bias? Answers like right here, it's forward bias, right? So it's 0.7, it's forward bias. So it's not in cutoff. You can right away eliminate that. Remember, chapter 1, if anode is higher than the cathode, it's forward bias. If cathode is higher, then it's reverse bias. So here it's an NPN transistor, right? NPN transistor. If P is higher than the N, then it's in forward bias, so it's not in cutoff. So that leaves us with either active or with saturation. So we check if the collector junction is forward bias. So the voltage at the collector junction is 4 volts. Base is 2 volts. NPN transistor. N is higher than P. Cathode is higher than the anode. That junction is reverse bias. So it's reverse bias. That again eliminates eliminates the saturation. So that leaves only active mode. Yes. No, that's just me making it easier to explain. That's just for explanation purposes, right? We haven't even begun any kind of basic analysis. I would not expect students to actually do this kind of analysis. All right, let's wrap this up. So we can test for saturation mode. Saturation mode, again, as I said, maximum current, then the voltage will be very, very low. Typically, that voltage between the collector and the emitter would be less than 0.4 volts, less than 0.4 between the collector and emitter, right here, okay, right between these 2 points, right? Because maximum current is flowing. So maximum current is flowing, what happens? Big voltage drop here, big voltage drop here, right? So that leaves very little voltage drop across the collector and emitter. You have free flow of currents going, almost like a short circuit. So we can check if the voltage between the collector and emitter is less than 0.4. That's another way of verifying saturation mode. It's not. It's 4 volts right here. It's 1.3, right? So it's 2.7 volts. So from that also, we can say that it is not in saturation, right? We already eliminated saturation in the previous, but this is just kind of like a verification or an alternative, if you will. Okay, so if it's not in saturation, then it's an active mode, right? All right, think on it. Let me know if you have any questions. There's a lot of information from today, so. Any questions from anyone? Yeah, homework is homework doesn't have this. This is, again, you have 3 modes. First thing to check is emitter base junction. If it's reverse bias or forward bias. If it's reverse bias, then it's just cut off. It's forward bias, then it's active or saturation. Then you check the collector junction. Collector junction forward bias is saturation. If it's reverse, it's active. And that's it. Yeah. All right. If there are no more questions, we'll end class here today. Did you have a question? Sure. Yeah, we can do it. Here. So the first step we did was we tested cutoff mode. Cutoff mode. We looked at the emitter base junction. So it's not reverse bias. So if it's not, actually, let's go back to the table right here. So we look at the table here. We first check the emitter base junction. If it's reverse bias, then right away we can say it's cut off, right? But if the emitter base junction is forward bias, then we have 2 choices, this or this, right? So then we checked. So in this circuit, again, we're not doing any analysis. The analysis is already done for us. These are the 3 voltages we are looking at: the base voltage, the collector voltage, and the emitter voltage. So we look at the base, we look at the emitter, we see that the base is higher than the emitter. VB is greater than V. Yes, so forward bias. Exactly. With forward bias, now we have 2 more choices. Now we look at the collector base junction. And the collector base junction, again, it's an NPN transistor. We have 4 volts at the N and 2 volts at the P. So it's reverse bias. So it's reverse bias, then it has to be active, cannot be saturation. So right away in these 2 steps, you already determined that it's an active mode. But there's a third way of checking, and that is if you want to test saturation mode directly, we can measure VCE. So if VCE is typically less than 0.4 volts, then the transistor would be in saturation because it's free flow of current. The high amount of current is flowing through, so voltage between collector and emitter will be very, very low. If the voltage is not low, as we see here, then it's not in saturation. It only leaves cutoff. It only leaves active. All right, make sense? All right. Okay. All right, we'll see you all on Friday. We'll continue with this CE amplifier, CE mode, and load line analysis. There'll be another homework based off of that. Today's homework is straightforward, shouldn't take you long. So if you get started while the material is fresh, you should be able to knock it out in like half an hour. All right, I'll see you all on Friday. Uh-huh. Saturday? Yeah. So